Hey guys, IBM is here with another episode of magnetic fields and electromagnetic induction. I think this is going to be part 27. So let's start from question 81. A coil of wire is situated in a uniform magnetic field of flux density B. The coil has a diameter 3.6 centimeters and consists of 350 turns of wire, as illustrated here. The variation with the time t of B is shown in the figure. So this is how B varies with time. So this is 0.2, this is 0.4, and this is, I think this is 45. Okay. Show that for the time t equals to 0 to time t equals to 0.2, the EMF induced in the coil is 0.080 volts. So that for the time t equals between time t equals 0 to time t equals 0.2, we know that induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is directly proportional to the gradient of the graph of B against time. So the induced EMF is equal to N B A over T. In this case, it will be N times A times change in B over change in T. And of course, we know that area equals to pi r squared. What is the radius? They gave us the diameter as 3.6, so the radius is 1.8 centimeters. So the induced EMF is going to be equal to, the number of turns was 350 times the area is going to be pi times 1.8 times 10 to the power of minus 2, but this should be squared, then times the gradient, change in B over change in T, that is 45 minus 0 over 0.2. So that is 45. That was millitesla, so that is 45 times 10 to the power of minus 3 divided by 0.2. So I'll say 45 exponent minus 3 divided by 0.2 times 350 times pi times 1.8 exponent minus 2 squared. So that is 0.08016 volts, which is approximately 0.080 volts. On the axis of the figures, 9.3 show the variation with the time t of the induced EMF E for time t equals to 0 to time t equals 0.8. So on the axis, we have to show the variation with the time t of the induced EMF. First of all, we have mentioned that induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is directly proportional to the gradient of the graph of B against T. Now, where the gradient is 0, the induced EMF is 0. That means between 0.2 to 0.4, we have a horizontal line for B, which means the magnetic flux linkage is constant, so the gradient there is 0. So the EMF represented by this in this time interval is going to be 0. That will be a horizontal line along the x-axis. So let me try to increase the font here. So between t equals to 0.2 and t equals to 0.4, the gradient was 0, so the induced EMF is 0. Then Between t equals to 0 to t equals 0.2, the EMF was 0.08, and because this gradient is constant, and because the line is a straight line, the gradient is constant, so the induced EMF is also going to be constant. So we shall represent that with a constant gradient, a constant induced EMF, which was actually 0.08. So on this scale here, each small box is 0.01. So 0.08 is going to be here. 0.08 is here. So 0.08 is here. So this is going to be that. Then we can check between t equals to 0.04 and 0.08. I want us to just compare the gradient. The gradient this side was 45 divided by 0.2. The gradient this side is 45 minus 0 divided by 0.4 to 0.8. That time interval is 0.4. So you notice that the gradient on the left hand side, is actually is 2 times. I think it's 2 times the gradient on the right hand side. We can check 45 divided by 0.2, that is 225, and 45 divided by 0.4, that is 112.5. So this gradient is half of this one. What does that mean? The EMF, if the EMF represented by this is 0.08, the EMF represented by this gradient is going to be 0.04. That is half of the EMF on the left hand side. So I'll represent this with 0.04, and I think 0.04 should be 1, 2, 3, 4. So 0.04 is here. 1, 2, 3, 4. Okay, so the graph would take this shape. Now, why is the graph below the x-axis? I want you also to notice that the gradient here was positive. The gradient this side is negative. So the EMF should have opposite signs. So the graph will take this shape. We can also swap the two sections. We make this section to be below the x-axis, and we make this section to be above the x-axis. As simple as that. A bar magnet is held a small distance above the surface of an aluminium disc by means of a rod as illustrated in the figure 9.4. The aluminium disc is supported horizontal and held stationary. The magnet is rotated about a vertical axis at a constant speed. Use laws of electromagnetic induction. When we talk about laws of electromagnetic induction, those are Lenz's laws and Faraday's law of electromagnetic induction. So use laws of electromagnetic induction to explain why there is a torque acting on the aluminium disc. So because the magnet is rotated about a vertical axis, the disc is going to cut the magnetic field lines of the magnet. So there is going to be a change in the magnetic flux, which is linked with the disc. And by Faraday's law, an EMF is going to be induced in the disc. And of course, the induced EMF is going to cause currents in the disc. The induced EMF is going to cause currents in the disc. These are the ones we call eddy currents. the current in the disk also creates its own magnetic field. So there are now two magnetic fields. One is caused by the current which has been induced in the disk, and the other one is a magnetic field due to the magnet itself. So these two are going to interact, and by Lenz's law, the two are going to oppose each other. So the current in the magnetic field of the magnet also causes a force on the disk, and thus this force may cause a torque to act on the disk. So we shall say that the disk cuts flux lines of the magnet. So there is a change, or there is a changing magnetic flux in the disk. There is a changing magnetic flux in the disks. Then by Faraday's law, an e.m.f is induced. In the disk. So whenever there is a change in magnetic flux, an e.m.f is induced. The induced e.m.f causes currents in the disk. The induced e.m.f causes currents in the disk. The current is in the magnetic field of the magnet. The current is going to be in the magnetic field. The induced current in the disk is also in the magnetic field of the magnet, which causes a force. Of course, whenever a current is in the magnetic field, there is a force on the conductor, which causes a force on the disk, and thus a torque or a moment. And thus a torque acts on the disk. So the current is in the magnetic field of the magnet, which causes a force on the disk, and thus a torque acts on the disk. Alternatively, the current in the disk also creates its own magnetic field, and when the two magnetic fields interact, there is a force exerted on the disk, which force causes a torque. An electron is traveling at a speed v in a straight line in a vacuum. It enters a uniform magnetic field of flux density 8.0 times 10 to the power of minus 4 teslas. Initially, the electron is traveling at right angles to the magnetic field as illustrated. So initially it is traveling at right angles to the magnetic field. If a particle travels perpendicular to the magnetic field, it experiences a magnetic force, whose direction is given by Fleming's left-hand rule. The path of the electron in the magnetic field is an arc of a circle of radius 6.4 centimeters. State and explain the direction of the magnetic field. So we have seen that the path is towards the bottom, which means the magnetic force is towards the bottom of the page at entry, at the point of entry. So remember, the magnetic force must be perpendicular to the path of the electron and also to the magnetic field. So if the force is downwards, the thumb must point downwards. Because the particle is an electron, using Fleming's left-hand rule, the second finger points in the opposite direction to that of the electron. Or the second finger is supposed to point in the direction of current or the direction of positively charged particles. So if we use Fleming's left-hand rule on a negatively charged particle, we reverse the second finger to point in the opposite direction. And when we do that, the first finger is going to be forcefully pointing into the page. Therefore, we shall say that the magnetic force is downwards. The magnetic force is downwards or down the page. The magnetic force is downwards or down the page, or you can say current is from, because the particles are moving from left to right, the current is from right to left. The current is from right to left in the opposite direction to the electrons. And by Fleming's left hand rule, the field is into the plane of the paper. By Fleming's left-hand rule, the field is into the plane of the paper. So do not forget to reverse the second finger when using Fleming's left-hand rule with the negatively charged particles, with the thumb down the page as illustrated here, and the second finger pointing the opposite direction to the current. The field is going to be into the plane of the paper or into the page. So also note that Fleming's right-hand rule could give us a result here, but when you use Fleming's right-hand rule, the second finger will point in the same direction as that of the electrons. Of course, the thumb is going to point downwards. Still, you notice that the first finger will point into the page. When you use the right-hand rule, do not reverse the second finger. When you use the right-hand rule, do not reverse the second finger. Show that the speed v of the electron is 9.0 times 10 to the power of 6 meters per second. Okay. So, of course, the magnetic force provides centripetal force. So I'll say magnetic force is equal to the centripetal force. So B QV is equal to mv squared over r. So the speed v is going to be equal to b qr divided by m. When we substitute, b was 8.0, then q is 1.6 exponent minus 19, radius is 6.4 centimeters, mass, we know the mass of an electron. So this is going to be 8.0 times 10 to the power minus 4, that was B. Charge of an electron 1.6 times 10 to the power of minus 19 coulombs. And the radius was 6.4 times 10 to the power of minus 2. Divide this by the mass, which is 9.11 times 10 to the power of minus 31. So 8 exponent minus 4 times 1.6 exponent minus 19 times 6.4 exponent minus 2 divided by 9.11 exponent minus 31. So that is 8.99 times 10 to the power of 6. Which is approximately 9.0 times 10 to the power of 6. A uniform electric field is now applied in the same region as the magnetic field to create what we call a crossed field. The electron passes undeviated through the region of the two fields. Remember, the magnetic force was downwards. For no deviation, the electric field force must be upwards. On the figure, mark with an arrow the direction of the uniform electric field. So, since the magnetic force is downwards in part A, then for no deviation, the electric force is going to be upwards, so that the electric force must be equal and opposite to the magnetic force for the particle to go through undeviated. I want you to also note that the electric force on a negatively charged particle acts in the opposite direction to the field. So if the force is upwards, it means the electric field should be downwards. So because the particle is negatively charged, the electric force is upwards, then the electric field is downwards. So the arrow for the electric field is going to be in this direction here, opposite to that of the electric force. If the particle is negatively charged, the electric field is in the opposite direction to the force, to the electric force on the particle. Use data from A to calculate the magnitude of the electric field strength. So, for no deviation, the magnetic force equals the electric force. That means B QV equals to Q times E. So the electric field strength is going to be B times V, which is going to be, I think B was 8.0 times 10 to the power of minus 4 teslas. And then V, what is V? V is 9.0 times 10 to the power of 6. So 9 exponent 6 times 8 exponent minus 4. So that is 7.2 times 10 to the power of 3. The electron in B is now replaced by an alpha particle traveling at the same speed v. It's an alpha particle. We know that the mass is 4u and the charge is 2e. The speed is the same v along the same initial path as the electron. Describe and explain the shape of the path in the region of the magnetic field. Now note that for no deviation, v equals to E over B, and this does not depend on the mass or the charge. What does that mean? Even though the alpha particle has a different mass and a different charge, as long as it has the same speed as the electron that we had before, it is still going to go through undeviated. So we shall say that the alpha particle also experiences no deviation. Experiences no deviation because the condition for no deviation only depends on speed v, and does not depend on mass or charge. So the speed, I mean the condition for no deviation is only depending on the speed. As long as the speed is equal to E over B, they said it is the same speed V that we got before. So it does not depend on the mass or the charge of the particle. A long straight vertical wire carries a current I. The wire passes through a horizontal card, EFGH, as shown in the figure here. On the figure, draw the pattern of the magnetic field produced by the current carrying wire on the plane EFGH. So make sure that when they ask you to draw a pattern, you draw at least 3 field lines, not less than 3. So imagine holding or gripping the conductor in your right hand with the thumb pointing the direction of the magnetic field. The magnetic field lines around the current carrying wire are concentric circles. So they are concentric circles around the wire. I always encourage my students to use a compass to make them very uniform. And then gripping the conductor with your right hand, the fingers fold in the anti-clockwise direction. So the field is in this direction here. Okay. Two long straight parallel wires P and Q are straighted a distance 3.1 centimeters apart, as illustrated in the figure. The current in wire P is 6.2 amperes. The current in wire Q is 8.5 amperes. The magnetic flux density B at a distance x from a long straight wire carrying a current I is given by the expression B equals to mu naught I over 2 pi x. Mu naught is 4 pi times 10 to the power of minus 7. It is not always given the list of constants because this was removed. But if it is needed for this particular question, it will be quoted for that matter. So I have quoted it here just to solve this question. The magnetic flux density at wire Q due to the current in wire P. Calculate the magnetic flux density at wire Q due to the current in wire P. So magnetic flux density is going to be equal to 4 pi times 10 to the power of minus 7, but it is due to the current in wire P. So we look for current in wire P, which is 6.2 divided by 2 pi times the separation of the two wires, which is 3.1 times 10 to the power of minus 2. So that is 4 pi exponent minus 7. Okay, so I'll say 4 exponent minus 7 times pi, then times 6.2. Anyway, pi cancelled. Why do I waste my time? Pi cancelled, 2 cancelled. So you have 2 exponent minus 7 times 6.2 divided by 3.1 exponent minus 2. So that is 4.0 times 10 to the power of minus 5 Teslas. The force per unit length in Newton per meter acting on wire Q due to the current in wire P. So the force is equal to B sine of theta. But of course, the magnetic field is in the horizontal plane and the current is in the vertical plane. So sine theta is going to be equal to 1 because theta is 90 degrees. Where wire Q, magnetic field is perpendicular to the current. So the force per unit length is going to be B times I, and B is this one here, 4 times 10 to the power of minus 5, and the current in wire Q, this is IQ. The current in wire Q was 8.5, so times 8.5. So that is 3.4 times 10 to the power of minus 4. The current in wires P and Q are different in magnitude. State and explain whether the forces per unit length on the two wires will be different. Of course, the forces are going to be the same. We said the force, you have seen that the force here, if I try to expand for you the force per unit length here, you have seen that the magnetic field B was equal to mu naught. The magnetic field due to the current in wire P. The magnetic field caused by wire P was mu naught times the current in wire P divided by 2 pi times x. Then the force on wire Q is equal to B caused by wire P, because the magnetic field of wire P is the one which spreads up to wire Q, then times the current in wire Q times the length. So that means that this is going to be equal to mu naught times, I'm substituting B, times IP over 2 pi x, then times IQ, then times L. So you see that the force depends on the product of the two currents. So the force is going to be equal. Force per unit length is going to be the same in magnitude. So I'll say the force per unit length is proportional to the product of both currents. So it's the same for both. It's the same for both wires. Or don't forget Newton's third law. Or by Newton's third law, the force or the forces per unit length are the same in magnitude, but in opposite directions. Okay, I think I want part 27 to stop at that point. See you in part 28. Until next time, bye bye.